Look at these three images. Whether painted with thick brushstrokes, geometric lines, or a patchwork of colors, your brain instantly recognizes a cat. This is qualia, an internal intuition allowing us to recognize catness even when details are distorted. A computer does not have qualia. It has no internal experience or intuition. When a machine scans a landscape, it does not conceptually see a mountain or a valley. To a machine, an image is a rigid grid of numerical values. It records the data with precision, but lacks the ability to interpret what those numbers represent. Generative art requires the artist to bridge the divide between human imagination and the machine's mathematical constraints. To understand those constraints, we have to look at how biological and machine vision differ. Biological vision is organic. Light passes through a lens and hits the retina, a light-sensitive layer of tissue at the back of the eye that is curved and uneven. The retina's cells are divided into rods for light intensity and cones for color. These cells are not arranged in a grid. They are scattered across the surface, more dense in some areas than others. Because of this biological structure, perception is relative. Depending on the specific layout of their cones, a human, a dog, and a whale look at the same landscape and see different colors and intensities. Biological vision acts as a subjective interpreter of the world, distinguishing it from engineered digital systems. A digital camera creates an image differently. Its lens focuses light onto a flat, two-dimensional array of electronic sensors. Each microscopic sensor acts as a photocell beneath a red, green, or blue filter. These cells convert incoming light photons into an electrical current. The amount of light striking the sensor dictates the size of the electrical voltage generated. A camera does not capture a scene. It records millions of isolated electrical measurements locked into a grid. This chart shows the response curve of a sensor. It highlights the first digital boundary, brightness. There is a floor where light is too dim to detect, and a saturation point where the sensor maxes out, recording pure white. The second boundary is color. Computers do not record continuous wavelengths. They use a 24-bit quantized system, mixing red, green, and blue values on a scale from 0 to 255. The third boundary is resolution. This is the minimum physical distance that can be observed, which dictates the area of the real world averaged into a single pixel. Zooming in on a digital photo does not reveal hidden details. It only enlarges the existing digital squares until the image breaks down into a grid. Every digital image is an approximation of reality, contained within these mathematical limits. A digital image is a two-dimensional spreadsheet of numbers. Every pixel in a photograph corresponds to a specific coordinate in a numeric matrix. A standard image contains millions of these coordinates, each holding a fraction of color data. Since the image is pure data, it is malleable. You are not painting on a fixed canvas. You are manipulating a database of color. This numeric structure allows the artist to manipulate every visual element through code. Processing is a language built to let artists command this mathematical grid without requiring a deep background in computer science. An artist uses specific syntax to declare a p-image, a built-in type that represents an image. This tells the computer to reserve memory for a new array of pixels. A single line of code can pull an image file into memory and display it on the screen. Once the data is loaded, the artist can write logic to target and overwrite the color value of any exact x and y coordinate. While the computer remains blind to the meaning of what it displays, the artist uses the logic of code to translate human imagination into a visual output.